So keeping in the theme of our limits topic, we have a theorem that helps us infer or imply the value of a limit given specific conditions. So this is called the Squeeze Theorem. So if we cannot find a limit directly, meaning using direct substitution or factoring, rationalizing, we may be able to find the limit indirectly with what's known as the Squeeze Theorem. Okay, and this theorem refers to a function f, or it could be labeled something else, but in this case we're saying f, whose values are squeezed between the values of two other functions, g and h. So I'm going to use the graph to the right to demonstrate. So here's g and here's h, and that's what I highlighted them on the graph. So if g and h have the same limit as x approaches some given c value, okay, then f will have that limit as well. Okay, so if I look at this graph, what they're saying is if you have a function on the top and a function on the bottom, and their limits as x is approaching some given c value, right here, is the same, and the f function is being squeezed in between, and you can see that all those are going towards the same value, then you can imply that f has the same limit. But the issue here is that you need to know specific information. Okay, so the Squeeze Theorem, which is also known as the sandwich or the pinching theorem, I've never seen this anywhere, I've only seen this, is as follows. If f of x falls between h of x, which is on the bottom, and g of x, which is on the top, okay, again, not always the same, but it's based on this graph, okay, for all given x in an open interval containing our value c, okay, except possibly at c itself, meaning it could be a hole, but remember that doesn't matter because we're evaluating the limit. And if the limit as x approaches c of h of x is equal to some given L value, and the limit as x approaches c of g of x is equal to that same value, meaning this one right here, so as x approaches c, this L value is my y, then the limit as x approaches c of f of x exists and would be equal to that same L value. Now, this right here is really important because this is going to be your hypothesis of the Squeeze Theorem. Okay, so this information is very important. Okay, so what I'm going to do is I'm going to show you on the top of the next page how this applies. Okay, so what we have in this example is some information, and this is how it would be given to you. So it says given f of x is equal to x squared minus 4x plus 7, and g of x is equal to the given polynomial, if h of x is a function that satisfies the following over the interval from 0 to 4, what is the limit as x approaches 2 of h of x? Okay, so there's a couple things that I need to point out here. First of all, in this problem, it does not specifically say, okay, using the Squeeze Theorem. But because we know now what the Squeeze Theorem says, meaning we have f of x above, because it's greater than h of x, and g of x is below, we're saying that h of x is between. So this right here is similar to the inequality, and this indicates the theorem. Okay, so this right here, this inequality with the three functions, indicates the Squeeze Theorem. So this is important that you know. In addition to that, they give you an interval, and the limit as x approaches some given value c has to be in that interval, and 2 falls in that interval. Okay, so that's what we have to look for. So for the hypothesis, what we have to show is that the upper and the lower limit, meaning this sandwich, the bread and the h of x is our meat. These two limits are the same. So what we're going to look at is our lower limit first, which is this lower one. So it's the limit as x approaches 2 of my g of x function. Okay, this is g of x. So I'll just put g of x here because we have it here. So what I'm going to use is direct substitution. So I plug in 2. So this is the opposite of 2 squared plus 4 times 2 minus 1. So this is negative 4 plus 8, so that would be 4 minus 1 is 3. Okay, and this is our lower function. Okay, g of x. Now what we have to look at is if I evaluate the limit as x approaches 2 of f of x, am I going to get 3? So you got to think about this graph right here. Are they going to the same value, the upper and the lower graphs? Okay, so we have the limit as x approaches 2 of f of x. This is our upper. Okay, so I look at f of x. So this is 2 squared minus 4 times 2 plus 7 is equal to. Okay, 2 squared is 4, right? Minus 8 is negative 4 plus 3, or excuse me, plus 7 is 3. So this is my upper function. Okay, so far we're in a good place. So what this means is my lower and my upper limits are exactly the same. And this inequality implies that h of x is squeezed in between these two. So this right here is my hypothesis. So this, because of this, I can write my conclusion, and it's based on this inequality here. Therefore, the limit as x approaches 2 of h of x is equal to 3 by the squeeze theorem. Okay, you need to state by the squeeze theorem. Okay? So I've shown you the generic form of the theorem, one that works. Now let's look to see what happens when one that doesn't work. Okay, so here you're given f of x, here you're given h of x. Do not freak out that it's a trig function. And it says if g of x is a function that satisfies the given inequality over the given interval, what is the limit as x approaches negative 2 of g of x, which is the middle. Okay, so this is my upper, this is my lower. Okay, h of x is less than g of x. All right, so what we want to do is evaluate the limit as x approaches negative 2. We're just going to say of h of x because it's right here. Okay, so I need to use this. So it's the cosine, I'm plugging in 2 for x, of 2 pi minus 2. Okay, cosine of 2 pi is a cosine of 0, which is 1. So this is 1 minus 2, so this is equal to negative 1. So this is the lower. Now we need to evaluate the limit as x approaches negative 2 of f of x. So I'm going to plug in negative 2. Should have been negative 2, but it's the same spot. Okay, so this is negative 2 squared plus 4 times negative 2 plus 5. Okay, so here we've got positive 4 minus 8 plus 5. So this is negative 4. This is equal to positive 1. This is our upper. So graphically what's happening is my h of x function is going to negative 1 and my f of x function is going to positive 1. So this fails. Okay, so here what I have to state, therefore the limit as x approaches negative 2 of g of x cannot be determined by the squeeze theorem. Okay, so what they said was that the g of x function fell between h of x and f of x. Unfortunately, what that means, though, based on my test, is that just because g of x is in the middle, it doesn't mean that you can use the squeeze theorem to determine what the limit is. it has to approach, your upper and your lower functions have to approach the same value when you're evaluating the limit.